So now we arrive at chapter 4, which is talking about the concept of threads. So why does a process actually needs threads? Basically, in a nutshell, we need threads because in order to make process much more manageable and easy to track. So for example, when you write a program, you write a program in different modules and you have different classes of execution for the instruction that you actually want to do. For example, you have a smaller task needs to be done. For example, collecting user data and then processing those data and also printing those data. So those smaller tasks are the reason why threads are being made from the main process. So for this chapter on threads, first of all, we are going to look at the relationship between process and threads, followed by the different approach in multi-threading, such as first of all, the single thread approach and also the multiple thread approach. So what is the relationship between process and threads? Is there any difference between a child process and a parent process? So now, here it is. So before we go further into the concept of a thread, we return back to the very basic concept of a process. Remember previously in the previous section where we look at the process that needs to be managed. In order to manage a process needs to actually give those information to the operating system. Means that what resources that it wants and what instruction that it needs to actually execute. So from that, the very basic of a process information is basically with regard to the resource ownership and also when does a process actually gets executed in the schedule. So that is a very basic thing that iOS needs in order to manage a process, and the process actually gives that information from the PCB, and then that PCB is relating those information in the OS control table. So with regard to the process and thread, just imagine a process as one big robot. Okay, so in this big robot, perhaps the function is for identifying new life form. Alright, so that is the very basic objective of this process. So in order to actually identify new life form to actually being safe, it needs to have the lightweight process comes in. So it needs to have perhaps an optic function, it needs to have a flying function, it needs to have a reporting function, for example. Alright, so this is where the thread or the lightweight process comes in. It is the building block that actually builds up this process altogether. So in order to identify a life form to save, it needs to have all those information being relayed back to the core programming of the process. So in this big robot, you have many smaller functions that helps it to actually function. You have the identifying module, you have the flying module, you have the pickup module, for example. So this is how a big unit can actually distribute smaller tasks to being done. And when it's done, okay, it will report back to the main process, and this process will actually report back to the OS. Alright, I have done this thing. Okay, I have finished processing this task or instruction. Then I can actually successfully end my instruction. So this is how a process and threads actually distribute its tasks. So by having threads, we give the ability of the operating system to execute multiple processes at the same time. It means that when the process executes, it doesn't necessarily have to execute in one linear way. So when one process actually being executed, another child process can execute in the background. So this actually saves time and resources for the process to actually wait for a certain result. So for example, if you have just one single thread, that single thread will need to actually be executed in a serial way. For example, it needs to detect thread, it also while waiting for the thread, it cannot do anything else, and then it waits for the result to detect the difference between a dirt and a non-dirt item, for example. And then it also needs to actually identify the dirt and then also wait for the status to be reported. Now, if you have a multi-thread approach, so this task can execute concurrently. Means it can execute at the same time and it does not actually wait to actually send the report to the operating system. So right now, for example, let's say this robot is actually waiting for the detection of dirt to be finished. And at the same time, it can also do other things. So let's say it identify 3 dirts. So while the first dirt is being identified and perhaps the second dirt has been identified and then the third dirt have not, so it can actually do processing on the second type of dirt and perhaps clean up the second dirt before the third dirt can actually be identified. So this saves time in also save between the decision between one task and another task, because the task do not actually have to wait for it to finish entirely before a next action can be executed. So now we look at an example perhaps in a single thread approach and also a multi-thread approach. In its simplest form, a single thread approach is where you can have only one instruction per cycle. One instruction, one process. So you cannot have multiple processes occurring at the same time. It is just like waiting for one process to finish entirely while the other process needs to be finished for the other process to actually comes in. So in this single-threaded approach, you cannot have multiple processes coming in because the task cannot be broken down into smaller pieces. So only if you have a child process and a parent process, do the task can be actually managed in a way where you have multiple paths for a multiple process. Because you need to actually wait for one process to finish entirely. Okay, the keyword is finish entirely until another process can actually comes in and actually being processed by the processor and be given the resource. So in contrast, in a multi-threaded approach, you can have one big process executing, and in the background you can have multiple child processes also executing. For example, when you open your Word application, for example, in the background you can have jobs such as doing backups for the currently written process, and you can also have spell checking, you can also do formatting, you can also do printing while also writing your report. So this was not actually accessible in the old days of the computer, where you have to actually finish writing your report and then only you do the printing process. So nowadays, we have multi-threaded approach in most of our process and program and application, which is very convenient to the users because we can actually do many tasks at the same time and also will not have to actually wait for another process to actually comes in for it to actually finish to actually opens another program. This is also true where you can have perhaps while writing, you can also open up your browser. So multi-threading actually helps assist the user where they can actually give the ability for the user to have a multitasking on different tasks. So for definition, in a multi-thread environment, a process is defined as the unit. Remember, we have the dispatching unit, we have the main unit. So each of these units is given a virtual address space that holds the process image. Remember, each process has their own process image, that is to tell the OS what is currently happening to the process. And also, this area given to the process image is protected and given only access to the permitted processes and also the given files and also the I/O resources. Just like when you understand the concept of single process, now in a multi-thread environment, this is also true where we identify each unit and the dispersing unit as the one single reference from the single ID. So you can have one, for example, 10 child processes, but identified by the child of which process. And each of those process and the child will be given proper address space and memory allocation together with the needed resources that it needs. So having said that, each thread, same as you have for a single process, so each thread also have their own execution state, their own context, their own execution stack, because they all have their instruction they need to actually do, and also they have the storage for local variables and also the access to memory. So whatever privilege that you are giving to a process, it is also true for a thread, except that a thread needs to report back to the main process because it is coming from them. So whatever a process needs to do, it will give to the related thread, and the thread will actually do it. So that's why what happens to a thread needs to be also keep track and report back, and whatever happens there will be monitored also by the operating system. So going back to the process that has no thread, okay, we look at the storage is one single memory block. So a single threaded process model have all those information, the PCB, the user stack, and whatever process image contained there, it is contained in a one single block. So whatever happens to the process is updated and then is being monitored by the operating system. So this is a very straightforward approach. Whereas in a multi-threaded approach, this block of PCB is further distributed into smaller blocks consisting of the thread status. So just as you have the PCB, now in a multi-thread approach, you have the thread control block, where each block actually reports what is happening to it, what it's currently doing, is it finished or not, which instruction. It's actually the same, but it's now broken down further into smaller portion of thread blocks. The concept is still the same. Ultimately, those TCB or thread control blocks will actually update to the PCB. Okay, it's just that in a multi-threaded approach, it permits actually happening or executing smaller portion of tasks and then ultimately being compiled back to the parent process in the process control block. So the benefit of a thread is basically very straightforward. First of all, it takes less time to create a new thread compared to creating a new process. It's because when actually you declare a process, the process actually declares what is needed. This includes what are the child process that is going to actually assist the parent process of what needs to be done. So whatever declaration for a process is actually related to all its child process. So that's why when you actually invoke the child process, it is much more faster than to actually create a new process altogether. And of course, less time to terminate and faster of switching between tasks within a single process, and also in terms of efficiency and communication between programs. Because basically you have this small task that can execute, and these tasks are actually reporting back to the parent process. So process can easily identify which tasks belong to which parent process, and also helps the OS to manage the terminating and creating new process very much faster and much more efficient. So here are some examples of thread usage that perhaps most of you are familiar with. So we can look at the use of the web browser, the word processor, and the web server. So for example, in the web server, you can actually open one thread to display image. You can also have one thread to actually manage the multiple tabs, and you can also perhaps play video at the same time in another tab. So this is one example of a multi-threading application. And also for word processor, like I said earlier, you can have one thread to actually display pictures, you can have one thread to actually read keystroke and interpret it, and you can have perhaps one also identify the mouse click. Okay, and then for web browser, one can have accepting user requests on the server, and then also another one is actually processing the request from another user. So these are just some of the examples. Okay, perhaps you can have much more. Okay, can identify anything that is actually using the multi-threading approach. Of course, nowadays it's very, you sometimes subconsciously already using it without you realizing it. That is actually a multi-threaded process in an application. So formally, where do we actually use threading in a single user system? So for example, we use it for foreground and also background work. So for foreground, for example, you are actually writing your Word application or spreadsheet, and in the background you have the autocorrect, or you have thesaurus, you have also the auto saving feature. So it helps having one happening in the foreground and another happening in the background. Another concept in a multi-thread system is that you can have actually asynchronous processing. Asynchronous means that while you are doing one task, you can have another task actually doing something else. So basically, for example, that previously you are typing, and then in the background you can have the backup coming in. Because sometimes you don't have to actually do backup all the time. Okay, you can set it as, let's say, for 5 minutes you do one backup of the file. So this helps if you have a multi-threaded program where you can set up the child process to actually do backup, while you can have another task actually do the typing and sending in information to the process. So this actually helps in terms of having a perceived time that is safe, meaning that you can actually have to do many things done at the same time without actually to manually do it all the time. So you don't have to actually, for example, keep pushing on the save button and just focus your attention to actually typing your report. And the third one is actually why we have a multi-thread approach. This is to actually help in terms of finishing up the process execution, because you have many threads executing at the same time, so you don't actually have to wait before another set of instruction can actually finish. Like I said earlier, so while typing, you can also have actually prepare another backup for it, and also periodically saving the files, and at the same time perhaps monitoring your spelling. So you don't have to manually do it one by one, because it is done throughout the process of what you are doing in the foreground. In the foreground, you are typing, and then in the background, it's actually do the backup and also checking your spelling, and also perhaps doing the formatting. So this can actually assist the user to actually do the task very fast on the computer, because you actually do many things at the same time. Sometimes you didn't actually realize that you are doing it, because this is actually being given to you in a multi-threaded system. So another advantage of having a threaded approach is that you can have a modular program structure. So nowadays you can have a team of programmers. So each team of programmers can focus on each of the different child process. For example, you can have one set of team just focusing on the spell checking, and then one set of team to actually do the backup, and then one set of team to do the formatting and perhaps image editing. So this can actually give an advantage to when you are writing a program, where those programs can actually be broken down into smaller pieces, and those smaller pieces can be actually independent while you are actually developing the program. And in terms of the data structure, remember in a process we have multiple states, so it is also true in a multiple thread setting. So if you have multiple state for your process, the same is also true in a thread setting. So most of the state information is actually maintained in a thread level data structure. Remember, in a multiple thread data structure, we have that PCB, and we also have the TCB. So whatever happened to the process and also to the related child process is updated from the TCB and then be given back to the PCB. So in terms of thread execution states, first of all, we look at the key states for a thread, which is the running, ready, and block. So if you remember, this running, ready, and block is for active processes. And of course, when active processes, okay, let's say you are a parent process. So you are giving some of the tasks to the child process. So while given the execution to a child process, so this operation then constitute to the change in the thread state. So in the thread state, you have the spawn, block, unblock, and finish. Spawn basically is an equivalent of the new thread for the parent process. But in terms of the thread, we name it as a spawn state. So once a process is being spawned, it is basically means that it needs to do something for the parent. So of course, we have the block and unblock because it's the same. Something is waiting for the thread, means that perhaps the thread is waiting for a resource, a thread is waiting for the user to enter certain data, so it is being blocked. So after the condition are met, it is being unblocked, and then after the task is finished, of course the state will be finished, and those updates will be sent back to the parent process. So for definition, we look back at these different thread states. For spawn, basically it is being initiated by a new process or by another thread within the process. And by blocking, it means that it's waiting for an event to happen. Unblock, event is actually happening and ready to be used. And then finish basically means that the child task is finished. The most important factor in having a multi-thread environment or a multi-thread approach is you need to ensure that there is synchronization between the threads. Because of course, ultimately, all the threads having those information in the TCB needs to report back to the PCB from the parent process. So without synchronization, of course, management of process can fail and the OS cannot actually allocate the correct resources to the correct thread from the correct process. So synchronization is very important in a multi-thread approach. So before we end this session, let's have a look back of what we have learned today. So first of all, we look at the concept of the process image, which contains all the necessary information for the OS to actually coordinate between the process. Also remember how this process is being used for the OS control table and also the PCB, and also the role of different OS mode of operation, why is it needed, and how does process switching and interruption actually occurs. This follows by the concept of security in an operating system, and then lastly the concept of process and threads. Okay, so you may review all these concepts before we end, and if you have any question, feel free to ask me. So I hope this has been very beneficial to you. So until the next session, okay, see you around.